Today in this session, we have two presenters with us, Dr. Omkarnath Verma and Dr. Rajiv Ranjan. I would like to introduce to you to Dr. Omkarnath Verma, sir, and he received his BSc and MSc degree from Allahabad University and subsequently a PhD degree in quantum physics from Indian Institute of Technology, Guwahati. Sir is a theoretical physicist and carries out research in the area of nonlinear quantum optics. It's giving me an immense pleasure to inform you that he completed his postdoc as a Serb National Postdoctoral Fellow in the Department of Physics, NIT Warangal. Sir is a faculty member at University of Allahabad presently and exploring his research in the area of structured light and its interaction with material media, which is the topic of today's talk. So I would like to hand over the stage from now onwards to Dr. Omkarnath Verma, sir.
Okay, good afternoon to all the professors, students. Thank you, Kavita, for your nice way of introduction. Let me thank Professor Saurav Rai for giving me the opportunity to present my work, and also would like to thank Kaustav Dey for this kind invitation to discuss my research. Let me now share my. Yeah, now you can see the lights.
Yes, yes. Okay.
Yeah, so I will be actually talking on the nonlinear interaction of structured light with matter at this today's webinar on this applied optics and photonics at the Department of Physics, NIT Warangal. Presently, I'm working in Allahabad University. So outline of the talk will be, first I will introduce about the structured light, different kind of structuring of the light, for example, intensity, phase structured light, polarization structured light, and then these how these structured light interact with media. Medium will be electromagnetically induced transparent media. It is a very well known technique in quantum optics, and we will see how intensity, phase, and polarization structured light interact with this kind of media. And then I'll conclude and also give some future plan I have. So basically, structured light basically refers to engineering of light in all its degree of freedom. In simple words, we can say that if you have a laser beam which is a Gaussian, we can structured in a different form. We can play with intensity structure. We can play with phase. So we can actually make it into a desired structure. So, for example, we can shape the laser light in time and frequency. For example, we can create short pulses, nanosecond, microsecond, or picosecond pulses. We can also tailor the light in spatial degree of freedom. For example, amplitude, phase, and polarization. They will vary with spatial points actually. So first in, if you talk about intensity structured light, we have, if you go and write down the Maxwell equation in free space, drive the Maxwell wave equation, and under the paraxial wave approximation, you can solve Helmholtz equation, and you will be having number of free space modes. For example, fundamental lowest order Gaussian mode. Then we can also have, depending upon the you know structure of your cavity, resonator cavity in a laser, you can have a Hermite Gaussian mode. You can also have Legre Gaussian mode. I will be talking in detail, and we can also have inch Gaussian modes also. We can also structured phase, and those kind of light beams are basically called optical vertex beams. And examples are Legre Gaussian mode, hypergeometric Gaussian modes. So I will be also talking about this to not really hypergeometric, but Legre Gaussian in detail. We can also uh, make the light, polarization structuring by using different optical components basically. And if you include the polarization, those kind of beams, they are called vector vertex beams actually. And these, there are two classes in that: cylindrical vector beams and concave beams. And slowly will be knowing in great detail. So if you talk about intensity structure light, we have a fundamental Gaussian mode, which most of the laser actually emit in lowest order Gaussian mode. It is very difficult to get other higher modes by using simple laser cavity. We have to, you know, create some outside cavity to generate other higher order. For example, Hermite Gaussian. If your laser resonator cavity have a rectangular symmetry, then you can have Hermite Gaussian modes. They are nothing but they are solution of paraxial wave equation, Helmholtz equation in free space. You can have a Legre Gaussian mode if your laser cavities basically are cylindrically symmetric. We can also write inch Gaussian modes in elliptical coordinate actually. And hypergeometric modes also we can have in cylindrical coordinates, but only thing is that we have to consider the functional behavior, which we will get the solution from, you know Helmholtz equation by putting hypergeometric function there. We can also have Wechsel modes, and they are actually 2D Helmholtz equation solution written in polar coordinates. So if you write Helmholtz equation in polar coordinate and try to solve it, you will get Bessel kind of function. So it is wave basically whose amplitude is described by a Bessel function. Airy modes also we can have from, if you have laser beam, you put in a circular aperture, you can generate the array, structures actually by using lasers. So, so these are the intensity. I am talking about intensity structured light by different shapes we can generate. So let's talk about fundamental Gaussian mode. So if you go and solve the paraxial wave equation in free space for lowest order Gaussian mode, we will get this kind of expression. See, now this field which is associated with Gaussian beam depends on the propagation direction axis z, as well as their transverse coordinate. R is here nothing but root of square root of x square plus y square. So it depends on x, y, and z. I have omitted the time dependency here. So you can also write time here and by putting exponential I omega t. So what I want to say, this is the single mode actually emitted by a laser, which is polarized in a single direction and having a single frequency. Now, if you propagate this in free space, actually the shape, the shape of this Gaussian mode, you can plot, you can take the square of this and you can plot it, you can see 3D intensity profile here. But you propagate, the shape of this Gaussian beam, will remain constant, but size will change. For example, if you have initially 10 micrometer, maybe at 5 centimeter you will be having 50 micrometer beam size. Shape will remain constant, but size will change. And you can also note that. So see here how bit is changing with the distance here as beam propagating in free space. People say that laser fundamental Gaussian mode laser emits basically nearly plane wave. They are not perfectly plane wave because they are still diverging. You can see here this is the beam size at particular some distance z. This is the radius of curvature. You can calculate at some particular distance, and this is the Rayleigh range. The within which actually the beam is not very much diverging. Actually, we can exclude the divergence. That is the Rayleigh range actually. So, and this omega zero is a beam based, calculated at z equals to zero. If you take a lens, focus the laser beam at the focus, you will be having minimum beam size. That is basically this base size. One important thing about this 3D and 2D the cross section profile, you can see most of the intensity of the light energy is confined to in the axial laser axis, around the laser axis here at the center. And if you go slowly away from the center, the energy is decreasing, intensity is decreasing. That's what it is a Gaussian function. So people initially used this because there is a, you can say, gradient, because now intensity is changing slowly as you go away from the center. So there is a gradient intensity, and there must be a gradient in a force, and that gradient in force basically you can trap a particle. So people, if you talk about the nowadays application, people trap the particle by using this gradient in intensity of this kind of fundamental Gaussian mode. So this has those kind of application. I will be also talking about optical tweezers by using vertex beams. So let's talk about other intensity basically structured like Hermite Gaussian modes. So if you go and uh, solve the Maxwell wave equation in free space, writing the rectangular coordinates here, so you will be having a solution which is nothing but Hermite polynomials in x and y directions here. But if you plot the intensity, take m equals to 0, n equals to 0, you will be having fundamental Gaussian mode. Sir, I am audible. Hello.
Yes, sir, you are audible.
Okay, thank you. So you will be having fundamental Gaussian mode. We can also structure this Hermite Gaussian mode by putting one of the parameters here, m and n non-zero. So if m is 0, n is non-zero, you will be having this. If m is 1, so basically E10, E1, E01, and then you will be having E11. So you can have desired profile of your laser, you know, by changing these parameters. We can excite actually, and these are possible in external laser cavities, and we can also generate by some other methods. Let's talk about Legre Gaussian structured light beam. If you put, that wave equation, you choose the cylindrical symmetric coordinates, you will be having a Legre polynomial there. But now, if you see in Legre the laser electric field associated with Legre Gaussian modes, there is a Legre polynomial, and there is a special type of functional behavior exponential I L phi. This gives actually some distinct behavior from the Hermite Gaussian mode here. So this L is with phi is basically azimuthal angle. L is azimuthal basically topological charge number. So now we can plot this and see the intensity, how intensity is changing, and we can structure light in different profiles as per our requirement. So if you put L equals to 0, E equals to 0, you will be having again fundamental lowest order Gaussian mode. If L is 1, you will be having a dark center surrounded by a high intensity profile here ring. So if you increase the L number but keeping P0, the radius of this dark center is increasing and you can go on. So people actually have used such kind of L equals to not 0 and P equals to 0 mode to create atomic waveguides. What is atomic waveguide? At the center where intensity is 0, basically the index will be high, and at the high intensity region index will be low. So it will be creating different index profile replicating that optical fiber. So they have used in that one also. We can create atomic waveguide for waveguiding of co-propagating other lights, pulses, maybe Gaussian modes. If you change now p coordinate, p parameters also, you can see now, and L is 0 here, but intensity at center becomes high and one dark ring. So what I want to say, we can structure light by using a laser which has a cylindrical symmetry, and we can have a desired profile of the intensity. And see, if you plot the phase profile of these beams, they are also distinct actually from each other. So they have unique character, and they will be basically orthogonal to, you choose any number here, and they will be always orthogonal to each other. So this will be, using in optical communication, you can have, if you have a huge amount of data you want to propagate, you can choose a different orthogonal modes and you can propagate them together. So because they are orthogonal, so they will be, there is no chance to interfere and lose of any information. So they are very helpful, Lagrangian mode. And I will be also discussing that this factor also plays very important role, and they will go for basically vortex bands. In Gaussian modes, I have taken this actually diagram from this reference. Anyone interested can go detail of this. I have taken expression from there. I have to go into detail of this. I have not derived it. I have done derivation for Gaussian, Hermite Gaussian, Lagrange Gaussian, but I have to see it. So, but I want to tell you, for ins Gaussian mode, you take the Gaussian mode, but that should be modified by 3 functions. Basically, it is making somewhat, to obtain paraxial wave equation in elliptical coordinates, we have to consider, complex envelope, which is modified version of Gaussian beam, and take it and put it back in Helmholtz equation, and you can find these two solutions, which is even and odd. And you can see here the, so because you are using fundamental, so these expressions can be again rewritten in Hermite Gaussian and basically Lagrange Gaussian in terms of those two independent modes. So you can see here also, you can have fundamental Gaussian, you can have Hermite Gaussian. So it is more general actually. In Gaussian modes are more general as compared to the others. They are basically third order. They form the third family of exact and orthogonal solution of wave equation. We have Gaussian, Hermite Gaussian, Lagrange Gaussian, and then we have in general in Gaussian mode. We have other beams, Bessel beams also. I have not included because anyone interested can go in detail of those. We have array beam, we have Matthew beams, the special kind of beam, Bessel beams. They are non-refracting beam. They have huge application because if you propagate all these modes I have talked, if they propagate in free space, they will be diverging. But if you talk about Bessel beams, they are not diverging actually. Their wavefront is created in such a way they will be reconstructing itself. So they have huge application in communication, free space communication. Excuse me. phase structure. Now, till now I have talked about only intensity, but so we can also play with the phase of the laser. How? So if you talk about the plane wave, in the plane wave or in Gaussian wave, we say that laser emits Gaussian and it is nearly almost a plane wave. Plane wave, basically they have infinite cross section, so they will not diverge. But in reality, laser is emits not a perfect plane wave; it is a Gaussian, so it will diverge basically. So they have plane. You can see here m equals to. So I will talk about what is optical versus. So for if you take this expression and you substitute m equals to l equals to 0 here, you will be having Gaussian. And Gaussian, if you say the helical this phase structure here, they are plane actually. But if we have a laser profile which has a functional behavior and azimuthal dependence like exponential IL phi, they will be having helical phase structure. Now phase is also structured. So depending upon the, so what is the, now coming to the point, what is the phase singularity and optical vertice? Optical vertices are nothing but a zero in optical field or a point of zero intensity. The phase actually, if you see at the zero intensity point, and Legre Gaussian is example of optical vertex, because at the center and the functional behavior is exponential IL phi, and the intensity at the center is zero. What is why phase singular? Because at that central point the phase is undefined. You cannot tell the phase information. You cannot get any phase information at the center. So, and phase, in the field circulates around these points of zero intensity actually. And why intensity at or field amplitude becoming zero? Because field is, the tip of electric vector is rotating on this basically phase profile, and at the center they will cancel to each other. So they will make the intensity at the center zero if you are having helical wavefront structure of laser beam. And L, what is the use significance L? L is called topological charge, signifying how many twists laser have actually in one complete wavelength. So if you have thing, this is actually in clockwise direction, but if you make it negative, it will be reverse in anti-clockwise direction. So you have plus and minus both. The the number, the higher number of the twists, the faster light is spinning around the axis. Now as you increase, the spin will be more. Here twist will be more. So how we can tell the number of these, whether this is +1, -1, and +2, -2? Is there is a very simple method. I have given two pictures here for extracting the topological charge information. So you take a Gaussian beam fundamental and a Lagrangian first order I have taken, and make them interfere. So you can have this kind of interference here. Now if you change the L value here, you will be having a different interference pattern here. So interfering of optical vortex with the Gaussian plane wave of light reveals the spiral phase as a constant concentric spiral. So basically here you can see here the number of arms in the spirals will give the information about topological charge. And the other diagram here, if you, this is exact axial interference, but if you little offset these two beams, Gaussian and this vortex beam, you can create the fourth kind of structure here. So for L equals to 1, you will be having one fork structure. Now if you change L value here, you will be having a different interference pattern here. So depending upon that fork profile, we can tell the, what is the basically topological charge of this vertex beam. So they can actually be generated by using different technique, special light modulators. We can also make the optical vertex by using Hermite Gaussian modes, because they can be used to generate Legre Gaussian, and Legre Gaussians are nothing but optical vertices. So now coming, one more important point to be noted here: the twisting of this kind of mode, carries orbital angular momentum associated with that basically wave. And if you put any dielectric particle in the path, it will exert a torque, because it is basically twisting or circulating around the axis. So it will have a huge application in optical tweezing technology. We can uh, confine a particle at the center. Even we can make them rotate if it has orbital angular momentum. Now, third class polarization structured light. Till now, I didn't talk about vectorial nature of laser light. Now we have to introduce vectorial nature of laser light. And polarization, inhomogeneous polarization and polarization singularities also I will tell. So now previously there was a scalar vortex beam, now there is a vector vortex beam. But if you want to generate the vector vortex beam, you need to have at least two modes here. Previously you can have a single mode. Now if you want to have a vector vertex means we have to take two modes, and they should basically, it is vector vertex film. They are vector sum of two field components with differing spatial properties, and they have also orthogonal polarization. So they will give new states of light, but the polarization will be varying point to point. I will show some of the simulation based on this equation. And this kind of vector vortex beam, they have v type of actually singularities, which are cylindrical vector vortex beams. So if you want to generate vector, so you take a laser, you take intensity and take two lasers. One is Legre Gaussian, choose L value. I am keeping P0 here. Radial index is 0, azimuthal index is -1. Along with this laser is left circularly polarized, and you have a second Legre Gaussian beam which has L value +1. Here is a -1, and this is right circular polarized. So they are basically orthogonal polarization. You see cosine gamma here and sine gamma, they can actually control the amplitudes here of these two modes. So we have a Legre Gaussian -1 with left, Legre Gaussian +1 with right polarization. If you take the superposition, you will be having vector vortex lights basically. One class is cylindrical vortex beams. If two circular polarizations have equal amplitudes, okay, amplitudes of their helicity. See, they are equal. Here one, here one. One is +1, opposite helicity. They are L also called helicity of the Legre Gaussian or vortex beams. So they are equal in magnitude but opposite in sign. The resulting beam will be cylindrically symmetric, vector beams, and they will span the equator of Poincare sphere. If you want to represent polarization, you have to calculate the polarization Stokes parameter. You can later represent them on Poincare sphere. So cylindrical vector beams, basically you can have them equator of Poincare sphere. Now from this, actually we can have radially polarized light. So beta is here, you see exponential I beta factor here. This is the telling the what is the phase difference between these two modes. Actually we can put beta equals to 0, pi by 2 in between also. So if you take beta equals to 0 in phase vector superposition of two scalar basically OM beams, with orthogonal polarization, you can create readily polarized light. Now if you choose beta equals to pi out of phase basically superposition, you will be having a smoothly polarized light. I will show them in detail next slide. Spiral, you can also create the spiral polarized beam by choosing this phase difference between these two, pi by 2 or plus or minus pi by 2. So we can have here. So before showing them what we have to do, if you have circularly polarized light, how will you uh, tell the polarization information about that beam? If it has a polarization character. So there is a called Stokes polarimetry, and we have to know about the Stokes parameters if you want to characterize a beam which has different kind of polarization, maybe linear, maybe circular, maybe elliptical. So in order to map the polarization distribution on the transverse plane, we use the 4 Stokes parameter in circular polarization basis. Actually, for different basis, these parameters will be different. So there is S1, S0, which tells total intensity here. This is the real part, S1, S2, and S3. One important thing, if you take S0 square and take S1 square plus S2 square plus S3, that will be equivalent to S0 square. S1 square, S2, S3, that will be S0. So it will be nothing but a sphere which has a radius 3 axes, S1, S2, S3, and this is will be the radius of that sphere. So we can represent any polarization state on Poincare sphere. And we can also tell the ellipticity of the polarization. We can also tell the ellipse orientation. Ellipticity means how well it is circularly polarized. This parameter will tell, or it is linearly polarized. So we will see all these information in coming slides. Hello, sir. I mean, you can listen me.
Yes, yes, Omkar.
Oh, okay. Thank you, sir.
Yes.
So now let's talk about sorry, readily polarized light. Other thing, this gamma I was telling, this gamma, cos gamma, or this thing only even cos theta, you can say other component of field EL sin theta. So by putting gamma different values, you can have different amplitudes. So we will be keeping at 45. So we will have 50% of X component, 50% Y component, and they are in phase. So here I have written actually expression. So Lagrangian left polarization with minus here helicity, and this is +1 with right helicity, and this is coming because 45 degree. So now we have here, so we have one mode here which is left circular, the other mode is right circular here. Now is superimpose these two, and by keeping their in phase relation, so you will be having interference. But if you go and do Stokes polarimetry, we can draw the polarization ellipses as each pixel position in cross section actually. So you can see this diagram here. We have plotted actually, you can see these dash lines, they are actually polarization ellipses. And you know that if you add a left circular polarization with the right one, it will be linear polarization actually. So that's what it is giving here. But you see that at the center, the intensity is 0 here. So because you know, they are vertex mode actually. Lagrangian, they are vertex mode. So, and if you see, you go any one direction, you will see the polarization is, going in radial direction, following a radial position from the laser axis here, any direction. So they are, the polarization ellipses are pointing in radial direction. That's why they are called radially polarized light. The important thing is the polarization vector across the beam is linear and make a constant angle with angle of 0 with radial direction. If you draw any line here, anywhere, you will be having, the linear polarization will be having basically 0 angle here. This is also shown in different kind of plots here. If you take x-axis here, y-axis here, and you draw a line of separation between, this color bar is showing basically 1 to 3 number. It is basically phase. It is basically phase profile. So basically polarization map actually. So it should be 0 to pi. Pi is 3 point something, so it is giving number 0 to. So you see 0 to 0 to pi. There is this line here. If you draw a line of separation between 0 to and pi, you will be seeing this. This is making with the x-axis. This is making 0 angle. That is signifying actually here what I have said. So that is the other way of saying. Next is azimutally polarized light. Now here see, uh, now you have to choose beta pi out of phase basically. They should, so if you take exponential I pi, you will be having a negative sign here. So still you have vortex mode here with negative velocity, minus 1, and here you have plus 1. And if you do the superposition, interfere them, you will be having, again a vortex mode. Along with, if you do the Stokes polarimetry, again you can plot the polarization ellipses and see their variation. They are basically changing in azimuthal direction here. If you follow, the polarization vector across the beam is linear. Obviously they are linear here, and it is coming from the expression, because if you add left circularly light with right one, you will be having linear polarization obviously. And if you draw any radial line from the center, any direction, so it is, you will see these polarization ellipses, they will make a constant angle of pi by 2. Here you can see the different way of saying here. This is x-axis and this is the line of separation. This makes angle, basically pi by 2 with respect to x-axis. Now we have a spirally polarized light. We can obtain them again if you take two components and those two are vertex with the negative one with the left polarization with and again now see that exponential I pi by 2, if you put, you can see here this plus I is coming and then you will be having minus I, and if you do the superposition you will be having sorry, I'll just take a little amount of water. So now if you do the superposition of these two, so you will be having spirally polarized light in clockwise direction. You can also changing the sign, you can create anti-clockwise direction. So you can follow here. So if you draw any radial line here in any direction, you will see the polarization is obviously linear, and that polarization ellipse will make angle of pi by 4 basically, um, with radial line and this ellipses, they make angle of pi by 4 here. And also the if you start, you can see that this polarization maps here. This is x-axis, this is y-axis, and this line of separation between 0 to pi actually makes angle of 45 with respect to x-axis. And also this angle of this polarization ellipses is increasing in if you go anti-clockwise direction from 0 to here is the reverse actually. So this is sorry, this is a clockwise actually, and this is anti-clockwise. We can follow a simple line here, and you can follow that path. It will direct to anti-clockwise. If you follow a single line here, and you will see this will go other direction. So we can also play with the polarization of light, and we can create a different structures actually by changing, uh, you know, their helicity, polarization, and all. Now coming to the next point, fully structured light. You will be having these such kind of beams basically are called Poincare beam. And such beams typically consist of vector superposition of two orthogonally LZ modes of different angular momenta. Please note that when I discussed the spiral or cylindrical vector beams, they had same magnitude of orbital angular momentum, one, but different sign actually. Here you will be having two modes, but different angular momenta. They cannot be 1 1 or 2 2. One, if one is 0, the other is 1. You can take 2 here. So what we have done here in case of so in previous case, if you see, radial polarized light, you have negative sign here, plus sign here. The total angular momentum will be 0. Same thing will also azimuthal, spiral also. But in case of fully structured light, because of two modes, two interfering modes, they have different orbital angular momentum. They can carry net angular momentum actually. 1 minus 0 will be 1, 2 minus 0. You will be having some definite value. These beams have polarization that varies in both. In previous case, cylindrical, you have radially polarized, azimuthal, and you have a spiral polarization. But this time, you will be having inhomogeneous polarization that will be both in the angular direction and radial directions also you will see. And the important point is the difference is they cover all polarization state on the Poincare sphere. Whereas the cylindrical vector ones, you can locate them, you can arrange them on equator. But here, in case of fully structured light, they will be covering nearly all the states on Poincare sphere. So the easiest way is creating them basically to have a fundamental Gaussian beam here with left circular polarization, and then you have here a radial, basically vertex mode here, Legre Gaussian first order, and with right circular polarization. The amplitude also you can control from here. So, but for simplicity, we will put here gamma equals to 45, and we can also put this phase difference, basically beta equals to 0. So basically, we will be creating polarization singularities. So in previous case, there is also a singularity in sorry, I didn't tell, but they have B type of singularities actually. In B type of singularities, actually, here, if you see the polarization at the center, polarization and orientation both are lost actually. We cannot tell the, so they have polarization similarity here. Here we have some different kind of, in case of Poincare beams, we have different kind of similarities basically. That is called C point similarities. I will tell when diagrams comes basically. So actually we cannot tell around this kind of similarity, we cannot tell the orientation of the ellipses, polarization ellipses. So if some information is lost at some point, that becomes singularity actually. For example, vertex beams at the dark center, we cannot have any phase information. So it is phase singular. Now this is a polarization singular actually. So this kind of singularities actually are made by the superposition of vertex mode of helical wavefront and a Gaussian mode. That's what it is written here. L0 is 00 is nothing but a fundamental Gaussian, and this first order actually. So Gaussian plane wavefront having orthogonal polarization. Please remember these two modes are always orthogonal. And this profile actually becomes multi-mode here because you are taking now two polarization states, left and right. One more thing here, now we have actually uh, three kind of point care beams: lemon, star, and moon star. So if you take lemon point care, it is a vector superposition of a vertex mode here with helical wavefront. This will give and a Gaussian mode of plane wavefront. These are orthogonal. So you, and keeping this gamma 45 beta 0, you can have a Lemon Poincare beams. Now if you reverse this for star, creating star Poincare beams, actually we can generate from Lemon itself. And but I'm telling, we can exchange this circular polarization, take this left to the helical wavefront, and this right circular to the basically Gaussian plane wavefront. So you can have star Poincare beams. Moon star actually, moon letter MON is coming from lemon MON, and star is coming from, so they are basically hybrid polarizations, singular topology that has properties of both lemon and star. In the coming slides, I will show them one by one. Pawan, still audible.
Yes, sir. You are audible.
Okay. Okay, thank you, thank you. Just I have to bake myself. So let's come
It's
to
fine.
the lemon Poincare beams. So such beams are typically consist of superposition of two orthogonalized LZ modes, but keeping one 0 0 without any orbital angular momentum. One is having some momentum here. So now if you superpose and do the polarimetry, you will see the lemon topology here. So now you have taken the Gaussian with left circular polarization. Actually, it is showing in some different, it should show in some different colors. I don't know it is visible or not, even I can. So we can actually do that. And this Legre Gaussian will have some right circular arc. So they will be having a different color. If you see carefully, they have actually. This is blue color, and this Gaussian one has left circular polarization with a red color here. So this is actually lemon topology here. Now you can see previously in cylindrical, you have only one polarization, that is a linear. Now here you can see you will have all polarization. You can see the linear polarization, you can have somewhere circular as well as elliptical polarization. So it is a fully structured light actually. And because it is covering whole sphere, and how you can differentiate it from others. So if you know draw a line by meeting all major axes of these ellipses, you will find a single line which meets, otherwise they will not meet. So in case of lemon, you will get a single line basically meeting all major axes of uh, polarization ellipses. So we can differentiate by drawing a streamline plot of such kind of topology here. Here also you see the polarization map of this topology. It is also going from 0 to pi. So each point here in this color is telling basically how the polarization ellipse orientation is basically changing. This streamline plots I have taken from this paper recently published by Hari Krishna in Dr. Saurabh Rai's lab. So this streamline plots gives clear distinction between lemon, star, and moon star topology. So here in case of lemon, you will be having single line here. And now coming to the star one, now we can have an interference here by changing left to right and right to left, or otherwise we can also change one thing from lemon. If you put this helicity of this vertex beam basically -1, then you can also have this star topology here. So now you do the interference here just for depiction I have shown, but this is the main diagram actually telling the information about left circular nature of Gaussian beam. Here now it is clearly visible. This is blue color actually. So it has a left circular, and these red polarization ellipses are coming because of this Lagrange Gaussian first order. So now here also at the C point, there is a singularity actually. Previously also at this point, we cannot tell the orientation or major axis, which direction it is oriented. Here also at the center, there is this circular polarization set, which we cannot tell what is the orientation of major axis of that one with respect to x-axis. So, and also if you want to differentiate it with other point pair beams, we can again plot the streamline plots. So previously we have a single line. Now here we can find 3 lines. How? We have to draw a line which meets all major axes in one direction. So you will, for star topology, you will having only three lines which will meet all the major axes in these directions. Otherwise, you will not get any straight line meeting with all major axes of these polarization ellipses. So this is also, so anyone interested can go more detail about this paper. This is excellent, and references therein. We can have lot of information actually. Moon star actually are created by introducing anisotropy parameter. You see exponential alpha here in vertex mode. Please remember, this is your Gaussian mode and this is vertex mode. So basically playing with the amplitude of the vertex mode generates a moon star. The combination of anisotropic vertex mode and a Gaussian mode of the orthogonal polarizations. These have left circular, this is we have right one, but there is some extra factor here sitting, exponential I alpha, and this is a phase difference already 0. So we can actually interfere them and create this moon star topology here. So again at the center, there is a C point singularity because we cannot tell the orientation of that major axis with respect to a x-axis. That is unknown actually. That's why it is polarization singular here. And from that C point, we can now, how can we differentiate this moon star with other point pair beams? So again, we have to draw lines meeting major axes in a single line. So you will be having 3 lines actually. They are pointed in the same direction, but here in case of star, you see they are going in different directions. Here they are nearly pointed in the same direction. So by this we can differentiate actually these 3 point pair beams. We can also create more
Yes, sir. It seems some problem is there. Sir, there is a problem with the Onkar sir network, sir. I think.
I think. Let wait. Keep
Yes,
quiet.
yes, sir. Yes, sir. I think sir will reconnect, sir. Sir left the meeting.
Okay. Hello, Dr. Rajiv Ranjan. So our next speaker also is here. So once Omkar finish, then we'll start the next talk immediately. Can any Sorry for the technical issue. We can wait for a while. By meantime, we are calling, trying to contact Dr. Omkar.
Hello, sir. Is there any some issue, sir? No, sir. Actually, you left the meeting and no screen is coming to us. Yes, sir. Please check it. Sir, I think sir didn't notice that internet connectivity is stopped.
I think so. He was giving this with this screen no presentation
Yes.
mode.
Yes, sir. Yes, sir. So, sir didn't notice that internet connection has lost. So, he'll be coming back.
Okay. Okay, Omkar, there was some technical problem. You switch on your audio, please. Dr. Omkar, you switch on your audio, please.
Yeah, sure.
Now it's audible. We are in the last slides that you are showing about monster mode. You show
Oh,
the
acha,
share the lights. Share the slides
uh,
once again. There was some breaking of internet, I think you said.
yeah. It's suddenly off. Okay, let me start. Is it visible, sir? Lights?
Yeah. Omkar, I hope we will take 10 more minutes to
Okay,
complete.
sir. Yeah.
Within 5-10 minutes, you please complete because
Yeah.
next.
Yes. Yeah. So, so, so you can have monster topology. Uh, Sir, my slide is visible.
Yes, it's
Okay.
visible. Just go.
So you can create by putting some anisotropy parameter here, uh, and you can do the polarization Stokes polarimetry, and you can draw the polarization ellipses. So if you draw, again a line, and by joining the major axes, you will find three lines three lines pointing in the same direction, which is, see, in case of star, it is going in all different directions, but here in case of one star, there will be three lines. They are actually infinite many lines, but three are measures here. So this will make the distinction from the others. So we will be using these structured light in our media called EIT. So EIT, basically, you can write down the Hamiltonian, all the frequencies, and you can put this Hamiltonian in, basically, this is Schrodinger equation. So if you want to solve the atomic dynamics, you have to solve the density matrix equation. You write the susceptibility and put those susceptibility expressions in basically Maxwell's wave equation in medium. And this is sitting parameter. So you can control basically any light wave propagating in medium. So this is the basically medium effect. So you can change the polarization effect, phase effects, and even you can reshape the laser beam by those things. So you can calculate density matrix, and in a steady state, you will can calculate all the parameters. See here, probe frequency sitting, control frequency, basically amplitude sitting here. So they all are here. So EIT is basically nothing making. If you suppose you don't have control light here, you simply propagate a laser light through a rubidium medium. So it will be absorbed, because if it is matching with this transition, it will be completely absorbed. And the dispersion, this is the imaginary part, this is the real part of the susceptibility. It is anomalous here. But if you put the control light here, you can reduce that absorption at the resonance here. You can see, and that this basically dispersion becomes normal here, which is used in steep. This is very steep and used in slow light propagation in case of propagation of pulses. So here I am giving the some flavor how we use Hermite Gaussian modes to propagate from one laser to the. We gave this Hermite Gaussian two mode, basically kidney shaped beam to control beam. While interaction, it is transferred to the cloning, means is basically imaging of control line to probe light. It is imaged here. Sir, it is still working.
Yes, yes.
Okay, okay. Okay. So here, and we can also have cloning of arbitrary images, basically. Uh, uh, in order to generalize the system, you have to propagate a multi-mode profile. So in your laser beams can be also saved in this form. Basically, you can put mask, you can create CPT kind of layers, and you can propagate. So so this was the first problem we have done, and the experimental verification came. They used the rubidium vapor here. Probe beam was there, and this is control beam here. They pushed mask. So this control beam is having U type of later structure, and probe beam is going there. So through interaction, it will be if there is no medium, it will be blurred. But if there is a medium, you will be having this kind of structure coming from this control laser to probe laser. So basically, we can do the imaging by using structured beam. We have used the Raman gauge system to image Lagrange beam mode. So this was the basically pump beam structure, and which is going to be transferred to the probe beam with very high resolution here. So we have used Lagrange Gaussian type of beam, and again we have used ARG kind of shaped laser shaped. mm, You know, if you put a mask writing ARG, so you will be having this kind of shaping, and you can propagate and have This was again experimental verification for Lagrange Gaussian mode actually, which was transferred from control beam to Stokes beam by this geometry. So recently we have also done very high order Hermite Gaussian modes in NIT Warangal itself. So we propagated this pump structure here, only two level system, because they are mutually interacting. So pump structure to be transferred to the probe beam, and we again simulated for some arbitrary mode, and that worked, and we have shown. So we will I am concluding here. So we discuss different kind of structuring of beam in different degree of freedom, space and time, intensity structure, Gaussian, Hermite Gaussian, Lagrange Gaussian, Bessel array, scalar vortex beams such as Lagrange Gaussian or hypergeometric Gaussian modes, which they carry orbital angular momentum. Discussed vector vortex beams also, including cylindrical Poincare beams we have discussed. They have huge application fusing, material processing, nanoscale imaging, tight field confinement, and also in optical communication and entanglement. Nonlinear ERT media and its interaction with light is shown. The only point is, in our research, we have not used cylindrical vector vortex beams or Poincare beams. So that we are trying to explore, and hopefully we will do it. Thank you for the patience.
Thank you, Dr. Omkarnath Verma. So there is we can go for some quick question answer session.
Yes.
There is a question by Kirti Ranjan Das. What are the methods to distinguish between LCP and RCP light waves? Left circular polarized and right circular polarized light waves.
How to?
What are the methods to distinguish between LCP and RCP of light waves?
Yeah, obviously, if we have such kind of lights, we can do the interference with simply a plane wave. So they will be having different this interference pattern. So we can identify. I gave the example of Lagrange Gaussian with +1 -1. By simply superposition with Gaussian, we can tell all the information, because they will be having different interference pattern. By we can create interference pattern, we can create the fork structure, and we can tell the all the +1 -1, all the topology. Actually, it can be done.
Nice. Any other questions? It can be directly asked to the speaker.
Yeah.
If not, then once again we thank Dr. Omkarnath Verma to covering a nice overview about different type of structured light beams and their